Welcome back, everybody. In this Python tutorial, we're going to go over how to create maps with GeoPandas. For install instructions, you can visit the GeoPandas documentation and then visit the installation page. Or you can create a GeoPandas package environment using the Anaconda Navigator. For the imports, we will import GeoPandas, pandas, geoplot, contextily, cartopy, matplotlib, and Folium. A key part of GeoPandas are geodataframes. GeoPandas geodataframes are like pandas dataframes with a geometry column. The geometry columns provide the geographic shapes, points, lines, polygons, etc. for the map. So here we have an example of a geodataframe, and you can see that it looks very much like a pandas dataframe with a geometry column here. To create this geodataframe, we use geopandas.readFile. Then inside the round brackets, we use geopandas.datasets.getPath. And then we pull in natural earth data for the world. You can also pull in geojson data to create a geodataframe. Here we have a path to some geojson data. Then we use geopandas.readFile. Then we put in the path. And here we have the geodataframe created from the geojson data. If you would like to create a geodataframe using a shapefile, you can do that as well. Once again, we have our path to the shapefile. Then we use geopandas.readFile and put in the path. And here is the geodataframe created from the shapefile. And just a quick reminder, one of the key parts of the geodataframe is the geometry column. Another thing you can do with GeoPandas is to convert pandas dataframes to a geodataframe. So here we have a path to a CSV file that includes latitude and longitude data. Using pandas.readCSV, we go ahead and create our pandas dataframe. Then to convert that to a geodataframe, we use geopandas.geodataframe. We put in the pandas dataframe, and for the geometry, we use geopandas.points from x, y. Then we put in the longitude and the latitude. And we can see that it creates the geometry column here. For our first example, we're going to use the world geodataframe that we created here, and it looks like this. To create a basic map, all we have to do is reference the world geodataframe. Then we use .plot, and we put in a fixed size of 15 by 10. And that gives us a basic map of the world. If you would like to visualize a specific geographic country or region, you can do that as well. So here, we use the world geodataframe. Then we set the index to the name. Then we use our regions variable, .loc. We put in the name of the region or the country, and then we reference the geometry column. And here we have the geographic boundary for Italy. Here we can see Ireland, Japan, India, and Egypt. And you should be able to visualize any country or region in your geodataframe. Next, let's go over an example of how to plot points. For our geodataframe, we're going to use some cities data. To create the geodataframe, we use geopandas.readFile. Inside the round brackets, we use geopandas.datasets.getPath, and the cities data is from natural earth. And we're just going to use a few records from this geodataframe. To plot the points for the cities on the map, the first thing we do is we create a figure and an axis using plt.subplots with a fixed size of 15 by 10. The plt.subplots creates a figure and a set of subplots. where the subplots defaults to 1. So basically, we create our figure and our plot, or subplot. And again, the ax, or axis, is the area, or subplot, on which to draw the plot. So the first thing we do is we create the world map using our world geodataframe.plot. And we assign ax to the ax argument. And again, that is the area, or subplot, on which to draw the plot. To plot the points for the cities, we use the cities geodataframe.plot. And since we want these to go on the same plot, or subplot, we assign ax to the ax argument. So in a way, assigning ax to the ax argument for both plots will give us layers. We have the world map, and then we have the dots with the cities. To create the labels for the dots, we use this code here, and we can see the labels here. Here we have a similar example. However, in this case, the size of the dots pertains to a data element in the geodataframe. The first thing we did is to create our figure and our plot, or subplot. To create the world map, we use world.plot, and the world map will be drawn onto our axis subplot. Then we use our tallest buildings geodataframe.plot, and the dots for the buildings will also go onto the axis subplot that we created here. We set the color to orange, and for the marker size, we use the tallest buildings geodataframe height column. So the bigger the circle, the taller the building. The alpha transparency is 0.5, and the edge color is black. And here we set a title for our figure. So this map shows you where the tallest buildings are in the world, and the size of the circle gives you an idea of how tall the building is relative to the other buildings. Let's go over how to create several different maps using subplots. We create our figure and our axes using plt.subplots. And inside the round brackets, we put the rows and the columns. So this will be a set of subplots that is 2 rows by 3 columns. Then we can filter the world geodataframe for each country we want to include. Now we can use the country or region variable .plot. And then for the ax argument, we determine which subplot we want the country to be drawn onto. So for example, this would be row 0 and column 0. And you can see we have Italy here. For Japan, this would be row 0, column 1. Here. For Egypt, it's row 0, column 2. And to explain further, this would be row 0, this would be row 1. This would be column 0, column 1, column 2. For India, it's row 1, column 0. For Argentina, it's row 1, column 1, here. And for Nigeria, it's row 1, column 2, here. And we use the same process to set the titles. If you wanted to, you could place more than one country onto the same subplot. Let's see an example where we will put Argentina and Nigeria onto the same subplot at row 1, column 1, here. So you can see Argentina and Nigeria. Next, let's go over an example of how to create a choropleth map. We create our figure and our plot. Then we use the Indiana County's geodataframe.plot. The map will be drawn onto our axis plot, here. And the key part of the choropleth map uses the column argument. And the data element we want to visualize is the population for 2020. For the color map, we're going to use cool warm. And we want the legend set to true, which will show us our color bar. And here we use the legend keyword argument shrink to shrink the color bar just a little bit. If we don't want to show the X and Y axis or the borders, we can use our plot.axis off. If that is on, it looks like this. Next, we have an example of grouping, specifically aggregation with dissolve. First, we create our figure and our plot. We only need these three columns from our data frame: continent, geometry, and population estimate. So we'll use the world data frame and filter it for these three columns and assign that to grouped. To create the continents, which will group the countries together, we use our grouped geodataframe, .dissolve. We want to group by continent. And for the aggregation function, we will use sum. To create the plot, we use our continents geodataframe, .plot. It's going to go onto our axis subplot, or plot. The column that we will use for the choropleth part of the map is the population estimate. For the scheme, we will use quantiles. If you would like to use a different scheme, there's a list of those here. For the color map, we're going to use reds, and the legend is set to true. You can see that here. Here we have an example of how to add a background map to your plots using contextily. Now, a quick note. Web map tiles are typically provided in Web Mercator projection. So for that, we will use the EPS G-code 3857. We create our figure and our plot. Then we use the Indiana Counties geodataframe. To convert this to the Web Mercator projection, we use 2CRS. CRS stands for Coordinate Reference System. Then we put in the EPS G-code 3857, and for the plot, we use .plot. We assign that to our subplot. The alpha transparency is 0.5 and the color is black. So that draws the Indiana Counties map. Then to add the base map, which you can see here, around the counties, we use the contextily package. Add base map. And we assign that to the same subplot as the Indiana counties. Let's go over how to filter your geodataframes to give you different types of maps. So in this example, we're going to filter our US states geodataframe to show us only the state of Indiana. We create our figure and our plot. Then we use the US states geodataframe, and specifically we're going to look at the state column. And we only want the data that equals Indiana. And to create the plot for Indiana, we use .plot. And you can see Indiana here. Next, now let's say that you only wanted to see states whose population is greater than 15 million. We create our figure and our plot. Then we use our US states geodataframe. And we're going to look at the population column. And we only want to include states whose population is greater than 15 million. And we assign that to a new variable called filter states. Then we use filter states.plot. And we can see that there's only 4 states whose population is greater than 15 million. California, Texas, New York, and Florida. Here we set a title and we turn the axis off. Notice there are points on the states. These are geocoded points. To create the geocoded points, we use geopandas.tools.geocode. Then we reference our filter states geodataframe .state column. For the provider, we use nominatum. For the user agent, we just put in tutorial. And we assign that to the variable locations. Then we use locations.plot. And that will plot the geocoded points that we see here in orange. And once again, if you would like to plot the labels, you can use this code here, which uses annotate. For our next example, let's go over how you can find centroids. Now, a quick note. In some cases, you may need to change a coordinate reference system for better correctness. And specifically, you may need to change the coordinate reference system from geographic to projected. However, from time to time, you may need to go from projected to geographic. So the first thing we did is we create our figure and our plot. And we're going to use the filter states geodataframe and convert that from a geographic CRS to a projected CRS using EPSG 5070. And we assign that to filter states albers, which stands for albers equal area. The next thing we did is we set the index to be the state. And that's just going to help us better see our results when we do some calculations. To create the plot, we use our geodataframe .plot. To find the centroids, we use our geodataframe .geometry.centroid. And to add the centroids to the map, we use centroids.plot. So a quick review on the coordinate reference system. From time to time, you may need to change your coordinate reference system. To do that, you can use your geodataframe .toCRS, and then you put in the EPSG that best suits your needs. And you may need to search the web to find the best EPSG. And, as far as I can gather, oftentimes, when you want to find centroids, or areas, or distances, you may need to change your CRS from a geographic to a projected. And we can see that the centroids are the dots in yellow. Now, one way to get more information on your geodataframe and to see the coordinate reference system details is to reference the geodataframe .CRS. So, for example, we can see that the original filter states geodataframe CRS information shows us that it is geographic. Now, recall that we converted the filter states geodataframe here and named it filter states albers. And the geodataframe should now be a projected CRS. We can see before it was geographic. And now it's projected. And for several of our examples, we will use projected when we want to get measurements or do calculations. And one last note before we move on. When dealing with projections in coordinate reference systems, it can be tricky. And normally what I do is I try out different things by searching the web to see what works. Next, let's go over an example of how to find distances between centroids. The first thing we did is we created our centroids, and we added it to our geodataframe. Here. To add the centroids, we use our filter states albers geodataframe. We added a new column, which will use the centroids. That we created here. And notice that the geodataframe can have more than one column with geometry in it. In this example, what we want to do is to find the distance from the Texas centroid to the centroids of California, Florida, and New York. So here we have created the centroid for Texas. Then to find the distances between the centroids, we use our filter states albers geodataframe using the centroid column. Then we use .distance, and we put in our Texas state centroid. And we run it, and we get the distances here. I believe these numbers are in meters. And here, we have converted those numbers in meters to miles. So, let's examine these distances. The distance from the Texas centroid to the Texas centroid is, of course, 0. The distance from the Texas centroid to the California centroid is about 1,200 miles. From the Texas centroid to the Florida centroid is about 1,000 miles. And from the Texas centroid to the New York centroid is about 1,500 miles. If you would like to find the area for the geographic regions, you can use your geodataframe.area. Now before we move on, let's try something real quick. Remember, for this, we're using the filter states albers that we created here, and we changed the CRS to projected. Now let's see what would happen if we just use the filter states. And you can see we get a warning. It says geometry is in a geographic CRS. Results from area are likely incorrect. And it says use geoseries to CRS to reproject the geometries to a projected CRS before this operation. So that's what we have attempted to do, to use to CRS to change it from geographic to projected. Now once again, I believe these numbers start out in meters squared. However, it would be nice to see those in kilometers squared or square miles. And to do that, we've used this code here. And that shows us the area for each of these states. Next, let's go over a buffer example. Buffer returns a geoseries of geometries representing all points within a given distance of each geometric object. And you can see here, with our maps, the red are the states, and the blue are the buffers. Now in this example, we're going to set some buffers, and then we want to see if any of the buffers intersect the state of Texas. So here we create a geodataframe, and we filter it for any states with a population greater than 15 million. Then we change the CRS on our geodataframe, just like we did before. And we set the index to the state name. Then we add a column to the geodataframe to create the geographic boundaries for the states. And to create the boundaries, we use the geodataframe.boundary. Then we set our buffer. And the buffer we set is 600,000 meters, or about 370 miles. Then we go ahead and plot our buffers. And here we plot the geographic boundaries for the states. Now, as we mentioned, we want to see if any of these buffers in the blue intersects the red Texas state boundary. So here we create a map of Texas. Now here, to determine if the buffer intersects with the state boundary, we use our geodataframe buffered column dot intersects Texas, using this Texas geometry here. If we look at the buffers, we can see that the only buffer that intersects the boundary of Texas is Florida. Now, of course, we're going to get true for Texas, because Texas intersects Texas. But then we also get true for Florida, which is the result that we said we should get. Next, let's go over an example of how to use Geopandas with Folium. So here, we create our Folium map. And we are going to overlay the Indiana counties onto the Folium map. So we can zoom in and zoom out. And we can also click on each county and see a pop-up with the county name. A quick note, Folium uses latitude and longitude, so we will use the EPSG 4326. So we start out with our Indiana counties geodataframe. Then we use 2CRS EPSG 4326, and we assign that to this new variable here. Then we use a for loop to loop over the data frame, using iter tuples. Using this code, we simplify the geometry. And one reason that you simplify the geometry is because if you don't, your geojson might not be able to be plotted onto the Folium map. Next, we convert our geometry to JSON. Then we convert our JSON to geojson. Using this code, we add our pop-up labels. Then we add the geojson to the map. And finally, we display the map. For our next example, we're going to go over how you can use Geopandas with cartopy. So the first thing we did is we created our coordinate reference system. Then we create our figure and our plot. And we use the subplot keyword argument projection, and we put in the CRS that we created here. Then we need to convert the coordinate reference system to be compatible with GeoPandas. And to do that, we use this code here. And finally, we create our plot using our axis subplot or plot dot add geometries. And inside the round brackets, we put in our geodataframe using the geometry column. And we assign our coordinate reference system. And here we have our map. Here we have an example using geoplot and subplots. And finally, if you would like to export GeoPandas data to other types of files, we have 3 examples of that here. Here we have created our geodataframe. To take the geodataframe to Excel, you can use this code here. You reference your geodataframe .to Excel, and then you put in the path of where you would like that to be saved. If you would like to export your geodataframe to geojson, reference your geodataframe.to file, put in the path of where you would like that to be saved, and then for the driver argument, we assign geojson. If you would like to export your geodataframe to a shapefile, reference your geodataframe.to file, put in the path, and then you can just leave out the driver because it defaults to shapefile. Let's run it. And we can see the files here. And if you wanted to quickly view the geojson file or the shapefiles, you can use Qgis. That's all we have for this tutorial. Join us again next time.